A photograph shows the head and part of the body of a lizard on a rock in a well-lit area. Figure 12. One in a gamma lizard basks in the sun. As its body warms, the chemical reactions of its metabolism speed up. Chapter outline. 12. 1 chemical reaction rates. 12. 2 factors affecting reaction rates. 12. 3 rate laws. 12. 4 integrated rate laws. 12. 5 collision theory. 12. 6 reaction mechanisms. 12. 7 catalysis. The lizard in the photograph is not simply enjoying the sunshine or working on its tan. The heat from the sun's rays is critical to the lizard's survival. A warm lizard can move faster than a cold one because the chemical reactions that allow its muscles to move occur more rapidly at higher temperatures. A cold lizard is a slower lizard and an easier meal for predators. From baking a cake to determining the useful lifespan of a bridge, rates of chemical reactions play important roles in our understanding of processes that involve chemical changes. 2 questions are typically posed when planning to carry out a chemical reaction. The first is, will the reaction produce the desired products in useful quantities? The second question is, how rapidly will the reaction occur? A third question is often asked when investigating reactions in greater detail. What specific molecular-level processes take place as the reaction occurs? Knowing the answer to this question is of practical importance when the yield or rate of a reaction needs to be controlled. The study of chemical kinetics concerns the second and third questions. That is, the rate at which a reaction yields products and the molecular scale means by which a reaction occurs. This chapter examines the factors that influence the rates of chemical reactions, the mechanisms by which reactions proceed, and the quantitative techniques used to describe the rates at which reactions occur. Learning objectives. By the end of this section, you will be able to define chemical reaction rate, derive rate expressions from the balanced equation for a given chemical reaction, calculate reaction rates from experimental data. A rate is a measure of how some property varies with time. Speed is a familiar rate that expresses the distance traveled by an object in a given amount of time. Wage is a rate that represents the amount of money earned by a person working for a given amount of time. Likewise, the rate of a chemical reaction is a measure of how much reactant is consumed or how much product is produced by the reaction in a given amount of time. The rate of reaction is the change in the amount of a reactant or product per unit time. Reaction rates are therefore determined by measuring the time dependence of some property that can be related to reactant or product amounts. Rates of reactions that consume or produce gaseous substances, for example, are conveniently determined by measuring changes in volume or pressure. For reactions involving one or more colored substances, rates may be monitored via measurements of light absorption. For reactions involving aqueous electrolytes, rates may be measured via changes in a solution's conductivity. For reactants and products in solution, their relative amounts, concentrations, are conveniently used for purposes of expressing reaction rates. For example, the concentration of hydrogen peroxide, H2O2, in an aqueous solution changes slowly over time as it decomposes according to the equation. 2H2O2, letter 1D44, letter 1D45E2, H2O, letter 1D459, plus O2, letter 1D454. The rate at which the hydrogen peroxide decomposes can be expressed in terms of the rate of change of its concentration, as shown here. Rate of decomposition of H2O2 equals minus change in concentration of reactant time interval equals minus H2O, 2 letter 1D461, 2 minus H2O, 2 letter 1D461, 1 letter 1D461, 2 minus letter 1D461, 1 equals minus delta H2O, 2 delta letter 1D461. This mathematical representation of the change in species concentration over time is the rate expression for the reaction. The brackets indicate molar concentrations, and the symbol delta, delta, indicates change in. Thus, H2O 2-letter 1D4611 represents the molar concentration of hydrogen peroxide at some time T1. Likewise, H2O 2-letter 1D4612 represents the molar concentration of hydrogen peroxide at a later time T2. And delta H2O2 represents the change in molar concentration of hydrogen peroxide during the time interval delta, that is, T2 minus T1. Since the reactant concentration decreases as the reaction proceeds, delta H2O2 is a negative quantity. Reaction rates are, by convention, positive quantities, and so this negative change in concentration is multiplied by -1. Figure 12.2 provides an example of data collected during the decomposition of H2O2. A table with 5 columns is shown. The first column is labeled time H, beneath it the numbers 0, 0, 6, 0, 12, 0, 18, 0, and 24 are listed. The second column is labeled H subscript 2 O subscript 2 mol/L. Below, the numbers 1, 0, 0, 500, 0, 250, 0, 125, and 0, 625 are double-spaced. To the right, a third column is labeled capital delta H subscript 2 O subscript 2 mol/L. Below, the numbers -0, 500 -0, 250 -0, 125, and -0. 62 are listed such that they are double-spaced and offset, beginning one line below the first number listed in the column labeled H subscript 2 O subscript 2 mol/L. The first two numbers in the second column have line segments extending from their right side to the left side of the first number in the third row. The second and third numbers in the second column have line segments extending from their right side to the left side of the second number in the third row. The third and fourth numbers in the second column have line segments extending from their right side to the left side of the third number in the third row. The fourth and fifth numbers in the second column have line segments extending from their right side to the left side of the fourth number in the third row. The fourth column is labeled capital delta T H. Below the title, the value 6 is listed 4 times, each single-spaced. The fifth and final column is labeled rate of decomposition, mol/L superscript -1/H superscript -1. Below, the following values are listed single-spaced: -0, 833 -0, 417 -0, 208, and -0. 10. Figure 12. 2. The rate of decomposition of H2O2 in an aqueous solution decreases as the concentration of H2O2 decreases. To obtain the tabulated results for this decomposition, the concentration of hydrogen peroxide was measured every 6 hours over the course of a day at a constant temperature of 40 degrees C. Reaction rates were computed for each time interval by dividing the change in concentration by the corresponding time increment, as shown here for the first 6-hour period. Minus delta H2O2 delta letter 1D461 equals -0, 500 mol/L -1, 0 mol/L, 6, 0 H -0. H equals 0, 833 mol LH. Notice that the reaction rates vary with time, decreasing as the reaction proceeds. Results for the last 6-hour period yield a reaction rate of minus delta H2O2 delta letter 1D461 equals -0, 0.625 mol/L -0, 125 mol/L, 24, 00 H -18, 00 H equals 0, mol LH. This behavior indicates the reaction continually slows with time. Using the concentrations at the beginning and end of a time period over which the reaction rate is changing results in the calculation of an average rate for the reaction over this time interval. At any specific time, the rate at which a reaction is proceeding is known as its instantaneous rate. The instantaneous rate of a reaction at time 0, when the reaction commences, is its initial rate. Consider the analogy of a car slowing down as it approaches a stop sign. The vehicle's initial rate, analogous to the beginning of a chemical reaction, would be the speedometer reading at the moment the driver begins pressing the brakes, T0. A few moments later, the instantaneous rate at a specific moment, call it T1, would be somewhat slower, as indicated by the speedometer reading at that point in time. As time passes, the instantaneous rate will continue to fall until it reaches 0, when the car or reaction stops. Unlike instantaneous speed, the car's average speed is not indicated by the speedometer, but it can be calculated as the ratio of the distance traveled to the time required to bring the vehicle to a complete stop, delta it. Like the decelerating car, the average rate of a chemical reaction will fall somewhere between its initial and final rates. The instantaneous rate of a reaction may be determined one of two ways. If experimental conditions permit the measurement of concentration changes over very short time intervals, then average rates computed as described earlier provide reasonably good approximations of instantaneous rates. Alternatively, a graphical procedure may be used that, in effect, yields the results that would be obtained if short time interval measurements were possible. In a plot of the concentration of hydrogen peroxide against time, the instantaneous rate of decomposition of H2O2 at any time t is given by the slope of a straight line that is tangent to the curve at that time, figure 12. 3. These tangent line slopes may be evaluated using calculus, but the procedure for doing so is beyond the scope of this chapter. A graph is shown with the label time h appearing on the x-axis and h subscript 2 O subscript 2 mol per L on the y-axis. The x-axis markings begin at 0 and end at 24. The markings are labeled at intervals of 6. The y-axis begins at 0. 0 and includes markings every 0, 200 up to 1. 0. A decreasing, concave up, nonlinear curve is shown, which begins at 1. 0 on the y-axis and nearly reaches a value of 0 at the far right of the graph around 24. On the x-axis, a red tangent line segment is drawn on the graph at the point where the graph intersects the y-axis at 1. 0. The slope is labeled as slope equals negative capital delta H subscript 2 O subscript 2 over capital delta T subscript 0 equals initial rate. A vertical dashed line segment extends from the left endpoint of the line segment downward to intersect with a similar horizontal line segment drawn from the right endpoint of the line segment, forming a right triangle beneath the curve. The vertical leg of the triangle is labeled capital delta, H subscript 2 O subscript 2, and the horizontal leg is labeled capital delta T. The slope is labeled as slope equals negative capital delta H subscript 2 O subscript 2 over capital delta T subscript 12 equals instantaneous rate at 12H. A second red tangent line segment is drawn near the middle of the curve at 12. On the x-axis, a vertical dashed line segment extends from the left endpoint of the line segment downward to intersect with a similar horizontal line segment drawn from the right endpoint of the line segment, forming a right triangle beneath the curve. The vertical leg of the triangle is labeled capital delta H subscript 2 O subscript 2, and the horizontal leg is labeled capital delta T. Figure 12.3. This graph shows a plot of concentration versus time for a 10M solution of H2O2. The rate at any time is equal to the negative of the slope of a line tangent to the curve at that time. Tangents are shown at t equals 0h, initial rate, and at t equals 12h, instantaneous rate at 12h. Chemistry in everyday life. Reaction rates in analysis. Test strips for urinalysis. Physicians often use disposable test strips to measure the amounts of various substances in a patient's urine, figure 12. 4. These test strips contain various chemical reagents, embedded in small pads at various locations along the strip, which undergo changes in color upon exposure to sufficient concentrations of specific substances. The usage instructions for test strips often stress that proper read time is critical for optimal results. This emphasis on read time suggests that kinetic aspects of the chemical reactions occurring on the test strip are important considerations. The test for urinary glucose relies on a two-step process represented by the chemical equations shown here. C6H12O6 plus O2 minus right minus 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 catalyst C6H10O6 plus H2O2. H2O2 plus 2 and minus plus 2H plus minus right minus 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 catalyst to H2O plus I2. The first equation depicts the oxidation of glucose in the urine to yield glucolactone and hydrogen peroxide. The hydrogen peroxide produced subsequently oxidizes colorless iodide ion to yield brown iodine, which may be visually detected. Some strips include an additional substance that reacts with iodine to produce a more distinct color change. The two test reactions shown above are inherently very slow, but their rates are increased by special enzymes embedded in the test strip pad. This is an example of catalysis, a topic discussed later in this chapter. A typical glucose test strip for use with urine requires approximately 30 seconds for completion of the color-forming reactions. Reading the result too soon might lead one to conclude that the glucose concentration of the urine sample is lower than it actually is, a false negative result. Waiting too long to assess the color change can lead to a false positive due to the slower, not catalyzed, oxidation of iodide ion by other substances found in urine. A photograph shows 8 test strips laid on paper toweling. Each strip contains 11 small sections of various colors, including yellow, tan, black, red, orange, blue, white, and green. Figure 12. 4 test strips are commonly used to detect the presence of specific substances in a person's urine. Many test strips have several pads containing various reagents to permit the detection of multiple substances on a single strip. Credit Iqbal Osman. Relative rates of reaction. The rate of a reaction may be expressed as the change in concentration of any reactant or product. For any given reaction, these rate expressions are all related simply to one another according to the reaction stoichiometry. The rate of the general reaction, RABB, can be expressed in terms of the decrease in the concentration of A or the increase in the concentration of B. These two rate expressions are related by the stoichiometry of the reaction. Rate equals minus 1A, delta a delta letter 1D461 equals 1B, delta B delta letter 1D461. Consider the reaction represented by the following equation. 2NH3, letter 1D454N2, letter 1D454, plus 3H2, letter 1D454. The relation between the reaction rates expressed in terms of nitrogen production and ammonia consumption, for example, is minus delta mol NH3 delta letter 1D461 times 1 mol and 22 mol NH3 equals delta mol N to delta letter 1D461. This may be represented in an abbreviated format by omitting the units of the stoichiometric factor. Minus 12 delta mol NH3 delta letter 1D461 equals delta mol N to delta letter 1D461. Note that a negative sign has been included as a factor to account for the opposite signs of the two amount changes. The reactant amount is decreasing, while the product amount is increasing. For homogeneous reactions, both the reactants and products are present in the same solution and thus occupy the same volume. So the molar amounts may be replaced with molar concentrations. Minus 12 delta NH, 3 delta, letter 1D461, equals delta N 2 delta, letter 1D461. Similarly, the rate of formation of H2 is 3 times the rate of formation of N2, because 3 moles of H2 are produced for each mole of N2 produced. 13 delta H, 2 delta, letter 1D461, equals delta N 2 delta, letter 1D461. Figure 12. 5 illustrates the change in concentrations over time for the decomposition of ammonia into nitrogen and hydrogen at 1100 degrees C. Slopes of the tangent lines at T equals 500 S show that the instantaneous rates derived from all 3 species involved in the reaction are related by their stoichiometric factors. The rate of hydrogen production, for example, is observed to be 3 times greater than that for nitrogen production. 291 times 10⁻⁶, letter 1D440/S9. 70 times 10⁻⁷, letter 1D440/S approximately 3. A graph is shown with the label time S appearing on the x-axis and concentration m on the y-axis. The x-axis markings begin at 0 and end at 2000. The markings are labeled at intervals of 500. The y-axis begins at 0 and includes markings every 1. 0 times 10 superscript -3, up to 40 times 10 superscript -3. A decreasing, concave up, nonlinear curve is shown, which begins at about 2. 8 times 10 superscript -3 on the y-axis and nearly reaches a value of 0 at the far right of the graph at the 2000 marking on the x-axis. This curve is labeled NH subscript 3. 2 additional curves that are increasing and concave down are shown, both beginning at the origin. The lower of these 2 curves is labeled N subscript 2. It reaches a value of approximately 1. 25 times 10 superscript -3 at 2000 seconds. The final curve is labeled H subscript 2. It reaches a value of about 3. 9 times 10 superscript negative 3 at 2000 seconds. A red tangent line segment is drawn to each of the curves on the graph at 500 seconds. At 500 seconds on the x-axis, a vertical dashed line is shown. Next to the NH subscript 3 graph appears the equation negative capital delta NH subscript 3 over capital delta T equals negative slope equals 1. 94 times 10 superscript negative 6m/s. Next to the N subscript 2 graph appears the equation negative capital delta N subscript 2 over capital delta T equals negative slope equals 9. 70 times 10 superscript negative 7m/s. Next to the H subscript 2 graph appears the equation negative capital delta H subscript 2 over capital delta T equals negative slope equals 2. 91 times 10 superscript negative 6m/s. Figure 12. 5 changes in concentrations of the reactant and products for the reaction 2NH3N2 plus 3H2. The rates of change of the three concentrations are related by the reaction stoichiometry, as shown by the different slopes of the tangents at T equals 500 s. Example 12. 1. Expressions for relative reaction rates. The first step in the production of nitric acid is the combustion of ammonia. 4NH3 letter 1D454 plus 5O2 letter 1D454, 4NO letter 1D454 plus 6H2O letter 1D454. Write the equations that relate the rates of consumption of the reactants and the rates of formation of the products. Solution. Considering the stoichiometry of this homogeneous reaction, the rates for the consumption of reactants and formation of products are minus 14 delta NH 3 delta letter 1D461 equals minus 15 delta O 2 delta letter 1D461 equals 14 delta NO delta letter 1D461 equals 16 delta H2O delta letter 1D461. Check your learning. The rate of formation of Br2 is 6 times 10⁻6 mol/L/S in a reaction described by the following net ionic equation. 5Br- plus Bro3- plus 6H plus 3Br2 plus 3H2O. Write the equations that relate the rates of consumption of the reactants and the rates of formation of the products. Answer. Minus 15 delta Br minus delta letter 1D461 equals minus delta Br. O3 minus delta letter 1D461 equals minus 16 delta H plus delta letter 1D461 equals 13 delta Br2 delta letter 1D461 equals 13 delta H2O delta letter 1D461. Example 12. 2. Reaction rate expressions for decomposition of H2O2. The graph in figure 12. 3 shows the rate of the decomposition of H2O2 over time. 2H2O to 2H2O plus O2. Based on these data, the instantaneous rate of decomposition of H2O2 at T equals 11. 1H is determined to be 3. 20 times 10⁻2 mol/L/H, that is, minus delta H2O 2 delta letter 1D461 equals 3. 20 times 10⁻2 mol L minus 1H minus 1. What is the instantaneous rate of production of H2O and O2? Solution. The reaction stoichiometry shows that minus 12 delta H2O, 2 delta, letter 1D461 equals 12 delta H2O delta, letter 1D461 equals delta O, 2 delta, letter 1D461. Therefore, 12 times 3. 20 times 10⁻2 mol L minus 1H minus 1 equals delta O, 2 delta, letter 1D461. And delta O, 2 delta, letter 1D461 equals 1. 60 times 10⁻2 mol L minus 1H minus 1. Based on the stoichiometry of this reaction as shown above, the rate of water product is therefore delta H2O delta letter 1D461 equals 2 delta O 2 delta letter 1D461 equals 2, 1. 60 times 10⁻2 mol L 1H1 equals 3. 20 times 10⁻2 mol L 1H1. Check your learning. If the rate of decomposition of ammonia, NH3, at 1150 K is 2. 10 times 10⁻6 mol/L/S, what is the rate of production of nitrogen and hydrogen? Answer. 15 times 10⁻6 mol/L/S, N2 and 3. 15 times 10⁻6 mol/L/S, H2. learning objectives. By the end of this section, you will be able to describe the effects of chemical nature, physical state, temperature, concentration, and catalysis on reaction, rates the rates at which reactants are consumed, and products are formed during chemical reactions vary greatly. 5 factors typically affecting the rates of chemical reactions will be explored in this section. The chemical nature of the reacting substances, the state of subdivision, one large lump versus many small particles of the reactants, the temperature of the reactants, the concentration of the reactants, and the presence of a catalyst. The chemical nature of the reacting substances, the rate of a reaction, depends on the nature of the participating substances. Reactions that appear similar may have different rates under the same conditions, depending on the identity of the reactants. For example, when small pieces of the metals iron and sodium are exposed to air, the sodium reacts completely with air overnight, whereas the iron is barely affected. The active metals calcium and sodium both react with water to form hydrogen gas and a base. Yet calcium reacts at a moderate rate, whereas sodium reacts so rapidly that the reaction is almost explosive. The physical states of the reactants, a chemical reaction between 2 or more substances, requires intimate contact between the reactants. When reactants are in different physical states, or phases, solid, liquid, gaseous, dissolved, the reaction takes place only at the interface between the phases. Consider the heterogeneous reaction between a solid phase and either a liquid or gaseous phase. Compared with the reaction rate for large solid particles, the rate for smaller particles will be greater because the surface area in contact with the other reactant phase is greater. For example, large pieces of iron react more slowly with acids than they do with finely divided iron powder, figure 12. 6. Large pieces of wood smolder, smaller pieces burn rapidly, and sawdust burns explosively. This figure shows 2 photos labeled A and B. Photo A shows the bottom of a test tube. The test tube is filled with a dark gas, and there is a dark substance and bubbles in the bottom. Photo B shows a rod and bubbles in a test tube similar to photo A, but the gas in the test tube is not as dark. Figure 12. 6a. Iron powder reacts rapidly with dilute hydrochloric acid and produces bubbles of hydrogen gas. Fe(S) plus HCl AC 2 FeCl2 AC plus 3H2G. B. An iron nail reacts more slowly because the surface area exposed to the acid is much less. Link to learning. Watch this video to see the reaction of cesium with water in slow motion, and a discussion of how the state of reactants and particle size affect reaction rates. Temperature of the reactants. Chemical reactions typically occur faster at higher temperatures. Food can spoil quickly when left on the kitchen counter. However, the lower temperature inside of a refrigerator slows that process so that the same food remains fresh for days. Gas burners, hot plates, and ovens are often used in the laboratory to increase the speed of reactions that proceed slowly at ordinary temperatures. For many chemical processes, reaction rates are approximately doubled when the temperature is raised by 10 degrees C. Concentrations of the reactants. The rates of many reactions depend on the concentrations of the reactants. Rates usually increase when the concentration of one or more of the reactants increases. For example, calcium carbonate, CaCO3, deteriorates as a result of its reaction with the pollutant sulfur dioxide. The rate of this reaction depends on the amount of sulfur dioxide in the air, figure 12. 7. An acidic oxide, sulfur dioxide combines with water vapor in the air to produce sulfurous acid in the following reaction. So 2 letter 1D454 plus H2O, letter 1D454H2SO, 3 letter 1D44E, letter 1D45E. Calcium carbonate reacts with sulfurous acid as follows. CaCO3, letter 1D460, plus H2SO3, letter 1D44E, letter 1D45E. CaSO3, letter 1D44E, letter 1D45E. Plus CO2, letter 1D454, plus H2O, letter 1D459, in a polluted atmosphere where the concentration of sulfur dioxide is high. Calcium carbonate deteriorates more rapidly than in less polluted air. Similarly, phosphorus burns much more rapidly in an atmosphere of pure oxygen than in air, which is only about 20% oxygen. A photograph is shown of an angel statue. While some details of the statue, including facial features, are present, effects of weathering appear to be diminishing these features. Figure 12. 7 statues made from carbonate compounds, such as limestone and marble, typically weather slowly over time due to the actions of water and thermal expansion and contraction. However, pollutants like sulfur dioxide can accelerate weathering. As the concentration of air pollutants increases, deterioration of limestone occurs more rapidly. Credit: James P. Fisher III link to learning phosphorus burns rapidly in air, but it will burn even more rapidly if the concentration of oxygen is higher. Watch this video to see an example. The presence of a catalyst relatively dilute aqueous solutions of hydrogen peroxide, H2O2, are commonly used as topical antiseptics. Hydrogen peroxide decomposes to yield water and oxygen gas according to the equation. 2H2O2, letter 1D44, letter 1D45E2H2O, letter 1D459, plus O2, G. Under typical conditions, this decomposition occurs very slowly. When dilute H2O2, AC is poured onto an open wound, however, the reaction occurs rapidly, and the solution foams because of the vigorous production of oxygen gas. This dramatic difference is caused by the presence of substances within the wound's exposed tissues that accelerate the decomposition process. Substances that function to increase the rate of a reaction are called catalysts, a topic treated in greater detail later in this chapter. Link to learning chemical reactions occur when molecules collide with each other and undergo a chemical transformation. Before physically performing a reaction in a laboratory, scientists can use molecular modeling simulations to predict how the parameters discussed earlier will influence the rate of a reaction. Use the pH at reactions and Rates Interactive to explore how temperature, concentration, and the nature of the reactants affect reaction rates. Learning objectives: by the end of this section, you will be able to explain the form and function of a rate law, use rate laws to calculate reaction rates, use rate and concentration data to identify reaction orders, and derive rate laws as described in the previous module. The rate of a reaction is often affected by the concentrations of reactants. Rate laws, sometimes called differential rate laws, or rate equations, are mathematical expressions that describe the relationship between the rate of a chemical reaction and the concentration of its reactants. As an example, consider the reaction described by the chemical equation letter 1D44E, letter 1D434, plus letter 1D44F, letter 1D435, letter 1D45D, letter 1D45F, letter 1D45C, letter 1D451, letter 1D462, letter 1D450, where A and B are stoichiometric coefficients. The rate law for this reaction is written as rate equals letter 1D458, letter 1D434, letter 1D45A, letter 1D435, letter 1D45B, in which A and B represent the molar concentrations of reactants, and K is the rate constant, which is specific for a particular reaction at a particular temperature. The exponents m and n are the reaction orders and are typically positive integers, though they can be fractions, negative, or zero. The rate constant K and the reaction orders m and n must be determined experimentally by observing how the rate of a reaction changes as the concentrations of the reactants are changed. The rate constant K is independent of the reactant concentrations, but it does vary with temperature. The reaction orders in a rate law describe the mathematical dependence of the rate on reactant concentrations. Referring to the generic rate law above, the reaction is M order with respect to A and N order with respect to B. For example, if M equals 1 and N equals 2, the reaction is first order in A and second order in B. The overall reaction order is simply the sum of orders for each reactant. For the example rate law here, the reaction is third order overall, 1 plus 2 equals 3. A few specific examples are shown below to further illustrate this concept. The rate law, rate equals letter 1D458H2O2, describes a reaction that is first order in hydrogen peroxide and first order overall. The rate law, rate equals letter 1D458C4H62, describes a reaction that is second order in C4H6 and second order overall. The rate law, rate equals letter 1D458H plus O minus, describes a reaction that is first order in H plus, first order in O minus, and second order overall. Example 12. 3 writing rate laws from reaction orders. An experiment shows that the reaction of nitrogen dioxide with carbon monoxide. No 2, letter 1d454, plus co, letter 1d454, no, letter 1d454, plus co 2, letter 1d454, is second order in no 2 and 0 order in co at 100 degrees C. What is the rate law for the reaction? Solution: the reaction will have the form rate equals letter 1d458 no, 2 letter 1d45a co letter 1d45b. The reaction is second order in no 2. Thus m equals 2. The reaction is 0 order in co. Thus n equals 0. The rate law is rate no co no. Remember that a number raised to the 0 power is equal to 1. Thus co 0 equals 1, which is why the co-concentration term may be omitted from the rate law. The rate of reaction is solely dependent on the concentration of no 2. A later chapter section on reaction mechanisms will explain how a reactant's concentration can have no effect on a reaction rate despite being involved in the reaction. Check you're learning the rate law for the reaction. H2, letter 1d454, plus 2 no, letter 1d454 ento, letter 1d454, plus H2, letter 1d454, has been determined to be rate equals K-No2H2. What are the orders with respect to each reactant, and what is the overall order of the reaction? Answer: order in No equals 2, order in H2 equals 1. Overall order equals 3. Check your learning in a transesterification reaction. A triglyceride reacts with an alcohol to form an ester and glycerol. Many students learn about the reaction between methanol, CH3OH, and ethyl acetate, CH3CH2OCOCH3, as a sample reaction before studying the chemical reactions that produce biodiesel. CH3OH plus CH3CH2OCOC3, CH3OCOC3 plus CH3CH2OH. The rate law for the reaction between methanol and ethyl acetate is, under certain conditions, determined to be rate equals letter 1d458CH3O. What is the order of reaction with respect to methanol and ethyl acetate, and what is the overall order of reaction? Answer: order in CH3O equals 1. Order in CH3, CH2OCOCH3 equals 0. Overall order equals 1. A common experimental approach to the determination of rate laws is the method of initial rates. This method involves measuring reaction rates for multiple experimental trials carried out using different initial reactant concentrations. Comparing the measured rates for these trials permits determination of the reaction orders and, subsequently, the rate constant, which together are used to formulate a rate law. This approach is illustrated in the next 2 example exercises. Example 12. For determining a rate law from initial rates, ozone in the upper atmosphere is depleted when it reacts with nitrogen oxides. The rates of the reactions of nitrogen oxides with ozone are important factors in deciding how significant these reactions are in the formation of the ozone hole over Antarctica, Figure 12. 8. One such reaction is the combination of nitric oxide, NO, with ozone, O3. A view of Earth's southern hemisphere is shown. A nearly circular region of approximately half the diameter of the image is shown in shades of purple, with Antarctica appearing in a slightly lighter color than the surrounding ocean areas. Immediately outside this region is a narrow bright blue zone followed by a bright green zone. In the top half of the figure, the purple region extends slightly outward from the circle, and the blue zone extends more outward to the right of the center as compared to the lower half of the image. In the upper half of the image, the majority of the space outside the purple region is shaded green, with a few small strips of interspersed blue regions. The lower half, however, shows the majority of the space outside the central purple zone in yellow, orange, and red. The red zones appear in the lower central and left regions outside the purple zone. To the lower right of this image is a color scale that is labeled total ozone, Dobson units. This scale begins at 0 and increases by 100s up to 700. At the left end of the scale, the value 0 shows a very deep purple color. 100 is indigo, 200 is blue, 300 is green, 400 is a yellow-orange, 500 is red, 600 is pink, and 700 is white. Figure 12. 8. A contour map showing stratospheric ozone concentration and the ozone hole. that occurs over Antarctica during its spring months. Credit: modification of work by NASA, No. letter 1D454, plus O3, letter 1D454, No. 2, letter 1D454, plus O2, letter 1D454. This reaction has been studied in the laboratory, and the following rate data were determined at 25 degrees C. Trial No mol/L, O3, mol/L, delta No 2 delta letter 1D461, mol L minus 1s minus 1, 1, 1, times 10 minus 6, 3, times 10 minus 6, 6, 60 times 10 minus 5, 2, 1, times 10 minus 6, 6, times 10 minus 6, 132 times 10 minus 4, 3, 1, times 10 minus 6, 9, times 10 minus 6, 1, 98 times 10 minus 4, 4, 2, times 10 minus 6, 9, times 10 minus 6, 3, 96 times 10 minus 4, 5, 3, times 10 minus 6, 9, times 10 minus 6, 5, 94 times 10 minus 4 determine the rate law and the rate constant for the reaction at 25 degrees C. Solution: the rate law will have the form: rate, No, O, determine the values of M, N, and K from the experimental data using the following three-part process. Step 1. Determine the value of M from the data in which No varies and O3 is constant. In the last three experiments, No varies while O3 remains constant. When No doubles from trial 3 to 4, the rate doubles, and when No triples from trial 3 to 5, the rate also triples. Thus, the rate is also directly proportional to No, and M in the rate law is equal to 1. Step 2. Determine the value of N from data in which O3 varies and No is constant. In the first three experiments, No is constant and O3 varies. The reaction rate changes in direct proportion to the change in O3. When O3 doubles from trial 1 to 2, the rate doubles. When O3 triples from trial 1 to 3, the rate increases also triples. Thus, the rate is directly proportional to O3, and N is equal to 1. The rate law is thus: rate No O No O, step 3. Determine the value of K from one set of concentrations and the corresponding rate. The data from trial 1 are used below. Letter 1D458 equals rate No O, 3 equals 6. 60 times 10 minus 5 mol L minus 1s minus 1, 1. 0, 0 times 10 minus 6 mol L minus 1, 3. 0, 0 times 10 minus 6 mol L minus 1 equals 2. 20 times 107 L mol minus 1s minus 1. Check your learning. Acetaldehyde decomposes when heated to yield methane and carbon monoxide according to the equation. CH3CHO, letter 1D454, CH4, letter 1D454, plus CO, letter 1D454, determine the rate law and the rate constant for the reaction from the following experimental data. Trial CH3CHO, mol/L minus delta CH3 CHO delta letter 1D461, mol L minus 1s minus 1, 1, 1. 75 times 10 minus 3, 2. 6 times 10 minus 11, 2, 3. 50 times 10 minus 3, 8. 24 times 10 minus 11, 3, 7. Times 10 minus 3, 3. 30 times 10 minus 10. Answer. Rate equals letter 1D458 CH3 CHO 2 with K equals 6. 73 times 10 minus 6 L/mol/S. Example 12. 5. Determining rate laws from initial rates using the initial rates method and the experimental data. Determine the rate law and the value of the rate constant for this reaction. 2. No, letter 1D454, plus Cl2, letter 1D454 2 knuckle, letter 1D454, trial No mol/L Cl2, mol/L minus delta No delta letter 1D461, mol L minus 1s minus 1, 1, 0, 10, 0, 10, 0, 302, 0, 10, 0, 15, 0, 453, 0, 15, 0, 10, 0. 675. Solution: the rate law for this reaction will have the form: rate equals letter 1D458 No letter 1D45ACl 2 letter 1D45B, as in example 12. 4. Approach this problem in a stepwise fashion, determining the values of M and N from the experimental data, and then using these values to determine the value of K. In this example, however, an explicit algebraic approach versus the implicit approach of the previous example will be used to determine the values of M and N. Step 1. Determine the value of m from the data in which no varies and CL2 is constant. Write the ratios with the subscripts x and y to indicate data from two different trials. R at t, e letter 1d465, R at t, e letter 1d466, equals letter 1d458 no letter 1d45a letter 1d465 CL, 2 letter 1d45b letter 1d465 letter 1d458 no letter 1d45a letter 1d466 CL, 2 letter 1d45b letter 1d466, using the third trial and the first trial, in which CL2 does not vary, gives rate 3 rate 1 equals 0, 6,750, 00300 equals letter 1d458, 0, 15, letter 1d45a, 0, 10 letter 1d45b letter 1d458, 0, 10 letter 1d45a, 0, 10 letter 1d45b, canceling equivalent terms in the numerator and denominator leaves 0, 6,750, 00300 equals 0, 15, letter 1d45a, 0, 10 letter 1d45a, which simplifies to 2, 25 equals 1. 5 letter 1d45a, use logarithms to determine the value of the exponent m, ln2, 25, ln2, 25, ln 1. 5 2 equals letter 1d45a ln 1. 5 letter 1d45a letter 1d45a, confirm the result 1. 52 equals 2. 25 step 2. Determine the value of n from data in which CL2 varies and no is constant. Rate 2 rate 1 equals 0. 4,500. 00300 equals letter 1d458, 0. 10, letter 1d45a, 0. 15, letter 1d45b letter 1d458, 0. 10 letter 1d45a, 0. 10 letter 1d45b cancellation gives 0, 450. 0030 equals 0. 15 letter 1d45b, 0. 10 letter 1d45b, which simplifies to 1, 5 equals 1. 5 letter 1d45b, thus n must be 1, and the form of the rate law is rate no CL. Step 3. Determine the numerical value of the rate constant, k, with appropriate units. The units for the rate of a reaction are mol/L/s. The units for k are whatever is needed, so that substituting into the rate law expression affords the appropriate units for the rate. In this example, the concentration units are mol3/L3. The units for k should be mol-2 L2s so that the rate is in terms of mol/L/s. To determine the value of k once the rate law expression has been solved, simply plug in values from the first experimental trial and solve for k. 0. 00300 mol L minus 1's minus 1 letter 1d458 equals letter 1d458, 0. 10 mol L minus 1, 2, 0. 10 mol L minus 1, 13. 0 mol minus 2 L to S minus 1, check your learning use the provided initial rate data to derive the rate law for the reaction whose equation is ACL minus, letter 1d44 letter 1d45e, plus I minus, letter 1d44 letter 1d45e oi minus, letter 1d44 letter 1d45e, plus CL minus, letter 1d44 letter 1d45e, trial ACL minus. Mol/L, I minus mol/L, initial rate mol/L/S, 10, 40, 20, 184, 20, 20, 40, 92, 30, 20, 20, 46. Determine the rate law expression and the value of the rate constant k with appropriate units for this reaction. Answer, rate 2 rate 3 equals 0. 920. 00046 equals letter 1d458, 0. 0020, letter 1d465, 0. 0040, letter 1d466, letter 1d458, 0. 0020, letter 1d465, 0. 0020, letter 1d466, 2 equals 2. 0 yy equals 1 rate 2 equals 0. 1840. 00092 equals letter 1d458, 0. 0040, letter 1d465, 0. 0020, letter 1d466, letter 1d458, 0. 0020, letter 1d465, 0. 0040, letter 1d46622. 4. 0, 0, letter 1 d465 equals 2 letter 1 d465 to y to x, 212 x2, substituting the concentration data from trial 1 and solving for k yields. Rate 0. 0, 0, 184 letter 1 d458 equals letter 1 d458 tackle minus 2 minus 1 letter 1 d458. 0. 0, 0, 20. 15. 75 times 104 mol minus 2 L to S minus 1 reaction order and rate constant units in some of our examples. The reaction orders in the rate law happen to be the same as the coefficients in the chemical equation for the reaction. This is merely a coincidence and very often not the case. Rate laws may exhibit fractional orders for some reactants, and negative reaction orders are sometimes observed when an increase in the concentration of one reactant causes a decrease in reaction rate. A few examples illustrating these points are provided. No 2 plus co to rate equals letter 1d458 no. 2 CH3 cho CH4 plus CR8 equals letter 1d458 CH. 3 chot 22 ento 5 no 2 plus O to rate equals letter 1d458 ento. 5 2 no 2 plus F2 2 no to freight equals letter 1d458 no. 2 F2 2 no to CL 2 no 2 plus CL to rate equals letter 1d458 no to CL. It is important to note that rate laws are determined by experiment only and are not reliably predicted by reaction stoichiometry. The units for a rate constant will vary as appropriate to accommodate the overall order of the reaction. The unit of the rate constant for the second-order reaction described in example 12, 4 was determined to be L mol minus 1's minus 1. For the third-order reaction described in example 12, 5, the unit for K was derived to be L to mol minus 2's minus 1. Dimensional analysis requires the rate constant unit for a reaction whose overall order is X to be L letter 1d465 minus 1 mol 1 minus letter 1d465s minus 1. Table 12. 1 summarizes the rate constant units for common reaction orders. Rate constant units for common reaction orders overall reaction order X. Rate constant unit Lx minus 1 mol 1 minus xs minus 1, 0, 0 mol L minus 1 s minus 1 1 first, s minus 1 2 second, L mol minus 1 s 3 third, L2 mol minus 2 s minus 1 table 12. One note that the units in this table were derived using specific units for concentration, mol/L, and time, s, though any valid units for these two properties may be used. Learning objectives by the end of this section, you will be able to explain the form and function of an integrated rate law, perform integrated rate law calculations for 0, first, and second-order reactions, define half-life, and carry out related calculations. Identify the order of a reaction from concentration time, data the rate laws discussed thus far relate the rate, and the concentrations of reactants. We can also determine a second form of each rate law that relates the concentrations of reactants and time. These are called integrated rate laws. We can use an integrated rate law to determine the amount of reactant or product present after a period of time, or to estimate the time required for a reaction to proceed to a certain extent. For example, an integrated rate law is used to determine the length of time a radioactive material must be stored for its radioactivity to decay to a safe level. Using calculus, the differential rate law for a chemical reaction can be integrated with respect to time to give an equation that relates the amount of reactant or product present in a reaction mixture to the elapsed time of the reaction. This process can either be very straightforward or very complex, depending on the complexity of the differential rate law. For purposes of discussion, we will focus on the resulting integrated rate laws for first, second, and zero-order reactions. First-order reactions integration of the rate law for a simple first-order reaction, rate equals Ka, results in an equation describing how the reactant concentration varies with time. Letter 1 D434 letter 1 D461 equals letter 1 D4340, letter 1 D452 minus letter 1 D458 letter 1 D461, where AT is the concentration of A at any time t. A0 is the initial concentration of A, and K is the first-order rate constant. For mathematical convenience, this equation may be rearranged to other formats, including direct and indirect proportionalities. ln, letter 1d434, letter 1d461, letter 1d4340 equals minus, letter 1d458, letter 1d461, ORLN. Letter 1d4340, letter 1d434, letter 1d461 equals, letter 1d458, letter 1d461, and a format showing a linear dependence of concentration in time. ln letter 1d434, letter 1d461 equals ln letter 1d4340 minus letter 1d458, letter 1d461, example 12. 6. The integrated rate law for a first-order reaction, the rate constant for the first-order decomposition of cyclobutane, C4H8 at 500 degrees C, is 9 2 times 10⁻³ S-1. C4H8 2C2H, for how long will it take for 80? 0% of a sample of C4H8 to decompose. Solution, since the relative change in reactant concentration is provided, a convenient format for the integrated rate law is ln, letter 1d4340, letter 1d434, letter 1d461, equals letter 1d458, letter 1d461, the initial concentration of C4H8, A0, is not provided, but the provision that 0% of the sample has decomposed is enough information to solve this problem. Let X be the initial concentration, in which case the concentration after 0% decomposition is 20. 0% of X or 200X. Rearranging the rate law to isolate T and substituting the provided quantities yields, letter 1d461 equals ln letter 1d4650. 200 letter 1d465 times 1 letter 1d458 equals ln 5 times 19. 2 times 10⁻³ minus 1 equals 1. 609 times 19. 2 times 10⁻³ minus 1 equals 1. 7 times 102. Check your learning. Iodine 131 is a radioactive isotope that is used to diagnose and treat some forms of thyroid cancer. Iodine 131 decays to xenon 131 according to the equation. I131 Z131 plus electron, the decay is first order with a rate constant of 0. 138 D-1. How many days will it take for 90% of the iodine minus 131 in a 500 m solution of this substance to decay to Z131? Answer: 16-7 days. In the next example exercise, a linear format for the integrated rate law will be convenient. ln letter 1d434, letter 1d461, letter 1d466 equals minus letter 1d458. Letter 1d461, plus ln letter 1d4340, letter 1d45a, letter 1d465, plus letter 1d44f. A plot of ln AT versus T for a first-order reaction is a straight line with a slope of -k and a y-intercept of ln A0. If a set of rate data are plotted in this fashion, but do not result in a straight line, the reaction is not first-order in A. Example 12. 7. Graphical determination of reaction order and rate constant show that the data in Figure 12. 2 can be represented by a first-order rate law by graphing ln H2O 2 versus time. Determine the rate constant for the decomposition of H2O2 from these data. Solution: the data from Figure 12. 2 are tabulated below, and a plot of ln H2O2 is shown in Figure 12. 9 time H2O2, M, ln H2O2 00100, 0600, 500 minus 0, 69312, 0250 minus 1, 386 1800, 125 minus 2, 7924, 00625 minus 2, 772. A graph is shown with the label time H on the x-axis and ln H subscript 2 O subscript 2 on the y-axis. The x-axis shows markings at 6, 12, 18, and 24 hours. The vertical axis shows markings at -3, -2, -1, and 0. A decreasing linear trend line is drawn through 5 points represented at the coordinates 0, 0, 6, -0, 693, 12, -1, 386, 18, -2, 79, and 24, -2, 772. Figure 12. 9. A linear relationship between LnH2O2 and time suggests the decomposition of hydrogen peroxide is a first-order reaction. The plot of LnH2O2 versus time is linear, indicating that the reaction may be described by a first-order rate law. According to the linear format of the first-order integrated rate law, the rate constant is given by the negative of this plot slope. Slope equals change I n letter 1 d466, ch, a n g, e I n letter 1 d465, equals delta letter 1 d466, delta letter 1 d465, equals delta H2, 2 delta letter 1 d461. The slope of this line may be derived from two values of LnH2O2 at different values of t. One near each end of the line is preferable. For example, the value of LnH2O2 when t is 0, h is 0. 0. The value when t equals 24. H is 772, SLOP, E letter 1d458 equals minus 2. 772 minus 0. 24. 0, 0 minus 0. H minus 2. 77,224. 0 H minus 0. 116 H minus 1 minus slope equals minus 0. 116 H minus 1 equals 0. 116 H minus 1, check your learning graph, the following data to determine whether the reaction letter 1d434, letter 1d435, plus letter 1d436 is first order. Time S A400 228, 00 14412, 00 110 16, 00 88 20, 00 74 answer. The plot of LNAT versus T is not linear, indicating the reaction is not first order. A graph, labeled above as ln a V's time, is shown. The x-axis is labeled time S and the y-axis is labeled ln a. The x-axis shows markings at 5, 10, 15, 20, and 25 hours. The y-axis shows markings at -3, -2, -1, and 0. A slight curve is drawn connecting 5 points at coordinates of approximately 4, -1, 8, -2, 12, -22, 16, -24, and 20, -26. Second-order reactions, the equations that relate the concentrations of reactants and the rate constant of second-order reactions, can be fairly complicated. To illustrate the point with minimal complexity, only the simplest second-order reactions will be described here, namely, those whose rates depend on the concentration of just one reactant. For these types of reactions, the differential rate law is written as rate equals letter 1 d458 letter 1 d4342. For these second-order reactions, the integrated rate law is 1 letter 1 d434 letter 1 d461 equals letter 1 d458 letter 1 d461 plus 1 letter 1 d4340. Where the terms in the equation have their usual meanings as defined earlier. Example 12. 8. The integrated rate law for a second-order reaction, the reaction of butadiene gas, C4H6, to yield C8H12 gas is described by the equation 2C4H6, letter 1D454, C8H12, letter 1D454. This dimerization reaction is second order with a rate constant equal to 5. 76 times 10⁻2 L mol minus 1 min minus 1 under certain conditions. If the initial concentration of butadiene is 0. 200 m, what is the concentration after 10? Min. Solution for a second-order reaction. The integrated rate law is written 1 letter 1 d434 letter 1 d461 equals letter 1 d458 letter 1 d461 plus 1 letter 1 d4340. We know three variables in this equation. A0 equals 0 200 mol/L, K equals 576 times 10⁻2 L/mol/min, and T equals 10. 0 min, therefore, we can solve for A, the fourth variable. 1 letter 1 d434 letter 1 d461, 1 letter 1 d434 letter 1 d461, 1 letter 1 d434 letter 1 d461 letter 1 d434 letter 1 d461 equals 5. 76 times 10⁻2 L mol minus 1 min minus 1. 10 min plus 10, 200 mol minus 1 5. 76 times 10⁻1 L mol minus 1 plus 5. L mol minus 15. 58 L mol minus 11. 79 times 10 minus 1 mol L minus 1, therefore 0, 179 mol slash L of butadiene remain at the end of 10 0 min, compared to the 0, 200 mol slash L that was originally present. Check your learning. If the initial concentration of butadiene is 0, 200 m, what is the concentration remaining after 20? 0 min, answer, 0. 195 mol slash L, the integrated rate law for second-order reactions, has the form of the equation of a straight line. 1 letter 1d434 letter 1d461 letter 1d466 equals letter 1d458 letter 1d461 plus 1 letter 1d4340 letter 1d458 letter 1d465 plus letter 1d44f. A plot of 1 letter 1d434 letter 1d461 versus t for a second-order reaction is a straight line with a slope of k and a y-intercept of 1 letter 1d4340. If the plot is not a straight line, then the reaction is not second order. Example 12. 9 graphical determination of reaction order and rate constant. The data below are for the same reaction described in example 12. 8. Prepare and compare 2 appropriate data plots to identify the reaction as being either first or second order. After identifying the reaction order, estimate a value for the rate constant. Solution time S, C4H6, M0, 1 times 10 minus 2, 1605. 4 times 10 minus 3, 3203. 37 times 10 minus 3, 4802. 53 times 10 minus 3, 6202. 8 times 10 minus 3, in order to distinguish a first-order reaction from a second-order reaction, prepare a plot of LNC4H60 versus T, and compare it to a plot of 1C4H6 letter 1D461 versus T. The values needed for these plots follow. Time S, 1C4H6 LNC 4H60 100 minus 4. 605, 1600 198 minus 5. 289, 3200 296 minus 5. 692, 4800 395 minus 5. 978, 6200 481 minus 6. 175, the plots are shown in Figure 12. 10, which clearly shows the plot of LNC4H60 versus T is not linear, therefore the reaction is not first order. The plot of 1C4H6 letter 1D461 versus T is linear, indicating that the reaction is second order. 2 graphs are shown, each with the label time S on the x-axis. The graph on the left is labeled ln C subscript 4H subscript 6 on the y-axis. The graph on the right is labeled 1 divided by C subscript 4H subscript 6 on the y-axis. The x-axes for both graphs show markings at 3000 and 6000. The y-axis for the graph on the left shows markings at -6, -5, and -4. A decreasing slightly concave up curve is drawn through 5 points at coordinates that are 0, -4, 605, 1600, -5, 289, 3200, -5, 692, 4800, -5, 978, and 6200, -6, 175. The y-axis for the graph on the right shows markings at 100, 300, and 500. An approximately linear increasing curve is drawn through 5 points at coordinates that are 0, 100, 1600, 198, 3200, 296, and 4800, 395, and 6200, 481. Figure 12. 10. These 2 graphs show first and second order plots for the dimerization of C4H6. The linear trend in the second order plot, right, indicates that the reaction follows second order kinetics. According to the second order integrated rate law, the rate constant is equal to the slope of the 1 letter 1D434 letter 1D461 versus T plot. Using the data for T equals 0s and T equals 6200s, the rate constant is estimated as follows. Letter 1D458 equals slope equals 481 letter 1D440 minus 1 minus 100 letter 1D440 minus 1. 6200s minus zeros equals 0. 0614 m minus 1s minus 1. Check your learning. Do the following data fit a second order rate law? Time S AM 50, 952 10 625 15 465 20 370 25 308 35 230 answer. Yes. The plot of 1 letter 1D434 letter 1D461 versus T is linear. A graph with the title 1 divided by A V's time is shown with the label time S on the x-axis. The label 1 divided by A appears left of the y-axis. The x-axis shows markings beginning at 0 and continuing at intervals of 10 up to and including 40. The y-axis on the left shows markings beginning at 0 and increasing by intervals of 1 up to and including 5. A line with an increasing trend is drawn through 6 points at approximately 4, 1, 10, 1, 5, 15, 2, 2, 22, 8, 26, 3, 4, and 36, 4, 4. Zero-order reactions. For zero-order reactions, the differential rate law is rate equals letter 1D458. A zero-order reaction thus exhibits a constant reaction rate, regardless of the concentration of its reactant, S. This may seem counterintuitive, since the reaction rate certainly can't be finite when the reactant concentration is 0. For purposes of this introductory text, it will suffice to note that zero-order kinetics are observed for some reactions only under certain specific conditions. These same reactions exhibit different kinetic behaviors when the specific conditions aren't met. And for this reason, the more prudent term pseudo-zero order is sometimes used. The integrated rate law for a zero-order reaction is a linear function. Letter 1D434, letter 1D461, letter 1D466 equals minus letter 1D458, letter 1D461 plus letter 1D4340, letter 1D458, letter 1D465 plus letter 1D44F. A plot of A versus T for a zero-order reaction is a straight line with a slope of minus k and a y-intercept of A0. Figure 12.11 shows a plot of NH3 versus T for the thermal decomposition of ammonia at the surface of two different heated solids. The decomposition reaction exhibits first-order behavior at a quartz CO2 surface, as suggested by the exponentially decaying plot of concentration versus time. On a tungsten surface, however, the plot is linear, indicating zero-order kinetics. Example 12. 10. Graphical determination of zero-order rate constant. Use the data plot in Figure 12. 11. To graphically estimate the zero-order rate constant for ammonia decomposition at a tungsten surface. Solution. The integrated rate law for zero-order kinetics describes a linear plot of reactant concentration, AT versus time, T, with a slope equal to the negative of the rate constant, minus k. Following the mathematical approach of previous examples, the slope of the linear data plot for decomposition on W is estimated from the graph. Using the ammonia concentrations at T equals 0 and T equals 1000 S, letter 1D458 equals minus slope equals minus 0. 0015 mol L minus 1 minus 0. 0028 mol L minus 1, 1000s minus 0 equals 1. 3 times 10 minus 6 mol L minus 1's minus 1. Check your learning the zero-order plot in Figure 12. 11 shows an initial ammonia concentration of 0. 28 mol L minus 1, decreasing linearly with time for 1000 S, assuming no change in this zero-order behavior. At what time, min, will the concentration reach 0? 1 mol L minus 1, answer, 35 min. A graph is shown with the label time S on the x-axis and NH subscript 3 m on the y-axis. The x-axis shows a single value of 1000 marked near the right end of the axis. The vertical axis shows markings at 10 times 10 superscript negative 3, 20 times 10 superscript negative 3, and 30 times 10 superscript negative 3. A decreasing linear trend line is drawn through 6 points at the approximate coordinates. 0, 2, 8 times 10 superscript negative 3, 202. 6 times 10 superscript negative 3, 400, 2, 3 times 10 superscript negative 3, 600, 20 times 10 superscript negative 3, 801. 8 times 10 superscript negative 3, and 1000, 16 times 10 superscript negative 3. This line is labeled decomposition on W. A decreasing slightly concave up curve is similarly drawn through 8 points at the approximate coordinates 0, 2, 8 times 10 superscript negative 3, 100, 2. 5 times 10 superscript negative 3, 200, 2, 1 times 10 superscript negative 3, 300, 1, 9 times 10 superscript negative 3, 400, 1. 6 times 10 superscript negative 3, 500, 1, 4 times 10 superscript negative 3, and 750, 1, 1 times 10 superscript negative 3, ending at about 1000, 0. 7 times 10 superscript negative 3. This curve is labeled decomposition on SiO subscript 2. Figure 12. 11. The decomposition of NH3 on a tungsten W surface is a zero-order reaction, whereas on a quartz CO2 surface, the reaction is first order. The half-life of a reaction, T12, is the time required for 1/2 of a given amount of reactant to be consumed. In each succeeding half-life, half of the remaining concentration of the reactant is consumed. Using the decomposition of hydrogen peroxide, figure 12. 2. As an example, we find that during the first half-life, from 00 hours to 6 hours, the concentration of H2O2 decreases from 10 m to 0. 500 m during the second half-life. From 60 hours to 12 hours, it decreases from 0, 500 m to 0, 250 m. During the third half-life, it decreases from 0, 250 m to 0, 125 m. The concentration of H2O2 decreases by half during each successive period of 60 hours. The decomposition of hydrogen peroxide is a first-order reaction, and, as can be shown, the half-life of a first-order reaction is independent of the concentration of the reactant. However, half-lives of reactions with other orders depend on the concentrations of the reactants. First-order reactions, an equation relating the half-life of a first-order reaction to its rate constant, may be derived from the integrated rate law as follows. ln letter 1 d4340, letter 1 d434, letter 1 d461, letter 1 d461, equals letter 1 d458, letter 1 d461, ln letter 1 d4340, letter 1 d434, letter 1 d461, times 1 letter 1 d458, invoking the definition of half-life. Symbolized T12, requires that the concentration of A at this point is 1/2 its initial concentration. Letter 1 d461 equals letter 1 d461, 1/2. Letter 1 d434, letter 1 d461 equals 12 letter 1 d4340. Substituting these terms into the rearranged integrated rate law and simplifying yields the equation for half-life. Letter 1 d461, 1/2, letter 1 d461, 1/2 equals ln letter 1 d4340, 12 letter 1 d4340, times 1 letter 1 d458 ln, 2 times 1 letter 1 d458 equals 0. 693 times 1 letter 1 d458 0. 693 K. This equation describes an expected inverse relation between the half-life of the reaction and its rate constant, K. Faster reactions exhibit larger rate constants and correspondingly shorter half-lives. Slower reactions exhibit smaller rate constants and longer half-lives. Example 12. 11. Calculation of a first-order rate constant. Using half-life, calculate the rate constant for the first-order decomposition of hydrogen peroxide in water at 40 degrees C. Using the data given in Figure 12. 12. A diagram of 5 beakers is shown, each approximately half filled with colored substances. Beneath each beaker are 3 rows of text. The first beaker contains a bright green substance and is labeled below as 1, 0M, 0S, and 0H. The second beaker contains a slightly lighter green substance and is labeled below as 0, 500M, 2, 16 times 10 superscript 4S, and 6H. The third beaker contains an even lighter green substance and is labeled below as 0, 250M, 4, 32 times 10 superscript 4S, and 12H. The fourth beaker contains a green-tinted substance and is labeled below as 0, 125M, 6, 48 times 10 superscript 4S, and 18H. The fifth beaker contains a colorless substance and is labeled below as 0625M8, 64 times 10 superscript 4s, and 24H. Figure 12. 12. The decomposition of H2O2, 2H2O2, 2H2O plus O2 at 40 degrees C is illustrated. The intensity of the color symbolizes the concentration of H2O2 at the indicated times. H2O2 is actually colorless. Solution inspecting the concentration time data in Figure 12. 12 shows the half-life for the decomposition of H2O2 is 2. 16 times 104s. Letter 1D461 1/2, letter 1D458 = 0. 693 K0. 693, letter 1D461 1/2 = 0. 6932. 16 times 104s = 3. 21 times 10 minus 5s minus 1. Check your learning. The first-order radioactive decay of iodine-131 exhibits a rate constant of 0. 138D-1. What is the half-life for this decay? Answer: 5,2D second-order reactions following the same approach as used for first-order reactions. An equation relating the half-life of a second-order reaction to its rate constant and initial concentration may be derived from its integrated rate law. 1 letter 1D434 letter 1D461 equals letter 1D458 letter 1D461 plus 1 letter 1D4340, or 1 letter 1D434 minus 1 letter 1D4340 equals letter 1D458 letter 1D461. Restrict T to T12 letter 1D461 equals letter 1D461 1/2. Define 8T as 1/2 A. Letter 1D434 letter 1D461 equals 12 letter 1D4340, and then substitute into the integrated rate law and simplify. 112 letter 1D4340 minus 1 letter 1D4340, 2 letter 1D4340 minus 1 letter 1D4340, 1 letter 1D4340, letter 1D461, 1/2 equals letter 1D458 letter 1D461, 1/2 letter 1D458 letter 1D461, 1/2 letter 1D458 letter 1D461, 1/21 letter 1D45. For a second-order reaction, T12 is inversely proportional to the concentration of the reactant, and the half-life increases as the reaction proceeds because the concentration of reactant decreases. Unlike with first-order reactions, the rate constant of a second-order reaction cannot be calculated directly from the half-life unless the initial concentration is known. Zero-order reactions, as for other reaction orders, an equation for zero-order half-life may be derived from the integrated rate law. Letter 1D434 equals minus letter 1D458 letter 1D461 plus letter 1D4340, restricting the time and concentrations to those defined by half-life. Letter 1D461 equals letter 1D461 1/2, and letter 1D434 equals letter 1D4340, 2. Substituting these terms into the zero-order integrated rate law yields A0, 2 letter 1D458 letter 1D461, 1/2 letter 1D461, 1/2 equals minus letter 1D458 letter 1D461, 1/2 plus A0, 2 letter 1D4340, 2 letter 1D458, as for all reaction orders. The half-life for a zero-order reaction is inversely proportional to its rate constant. However, the half-life of a zero-order reaction increases as the initial concentration increases. Equations for both differential and integrated rate laws and the corresponding half-lives for zero, first, and second-order reactions are summarized in Table 12. 2. Summary of rate laws for zero, first, and second-order reactions, zero-order, first-order, second-order. Rate law rate equals K rate equals Ka. Rate equals Ka2 units of rate constant ms minus 1s minus 1m minus 1s minus 1. Integrated rate law letter 1D434 equals minus letter 1D458 letter 1D461 plus letter 1D4340. ln letter 1D434 equals minus letter 1D458 letter 1D461 plus ln letter 1D4340, 1 letter 1D434 equals letter 1D458 letter 1D461 plus 1 letter 1D4340. Plot needed for linear fit of rate data AVs. T ln A, versus T 1 letter 1d434. Versus T relationship between slope of linear plot and rate constant k equals minus slope k equals minus slope k equals slope half-life letter 1d461 1/2 equals letter 1d4340 2 letter 1d458 letter 1d461 1/2 equals 0. 693 k letter 1d461 1/2 equals 1 letter 1d4340 letter 1d458 table 12. 2. Example 12. 12 half-life for zero-order and second-order reactions. What is the half-life for the butadiene dimerization reaction described in example 12? 8. Solution: the reaction in question is second-order, is initiated with a 200 mol L-1 reactant solution, and exhibits a rate constant of 576 L-mol-1 min-1. Substituting these quantities into the second-order half-life equation, letter 1d461 1/2 equals 1, 0. 576 L-mol-1 min-1, 0. 200 mol L-1 equals 86. 8 min. Check your learning. What is the half-life min for the thermal decomposition of ammonia on tungsten? See example 12. 10. Answer. 18 min. Learning objectives. By the end of this section, you will be able to use the postulates of collision theory to explain the effects of physical state, temperature, and concentration on reaction rates, define the concepts of activation energy and transition state, use the Arrhenius equation in calculations relating rate constants to temperature. We should not be surprised that atoms, molecules, or ions must collide before they can react with each other. Atoms must be close together to form chemical bonds. This simple premise is the basis for a very powerful theory that explains many observations regarding chemical kinetics, including factors affecting reaction rates. Collision theory is based on the following postulates. The rate of a reaction is proportional to the rate of reactant collisions. Reaction rate proportional collision time, the reacting species must collide in an orientation that allows contact between the atoms that will become bonded together in the product. The collision must occur with adequate energy to permit mutual penetration of the reacting species. Valence shells so that the electrons can rearrange and form new bonds and new chemical species. We can see the importance of the two physical factors noted in postulates 2 and 3. The orientation and energy of collisions, when we consider the reaction of carbon monoxide with oxygen. 2CO, letter 1d454, plus O2, letter 1d4542, CO2, letter 1d454. Carbon monoxide is a pollutant produced by the combustion of hydrocarbon fuels. To reduce this pollutant, automobiles have catalytic converters that use a catalyst to carry out this reaction. It is also a side reaction of the combustion of gunpowder that results in muzzle flash for many firearms. If carbon monoxide and oxygen are present in sufficient amounts, the reaction will occur at high temperature and pressure. The first step in the gas phase reaction between carbon monoxide and oxygen is a collision between the two molecules. CO, letter 1d454, plus O2, letter 1d454, CO2, letter 1d454, plus O, letter 1d454. Although there are many different possible orientations the two molecules can have relative to each other, consider the two presented in Figure 12. 13. In the first case, the oxygen side of the carbon monoxide molecule collides with the oxygen molecule. In the second case, the carbon side of the carbon monoxide molecule collides with the oxygen molecule. The second case is clearly more likely to result in the formation of carbon dioxide, which has a central carbon atom bonded to two oxygen atoms, O equals C equals O. This is a rather simple example of how important the orientation of the collision is in terms of creating the desired product of the reaction. A diagram is shown that illustrates two possible collisions between CO and O subscript 2. In the diagram, oxygen atoms are represented as red spheres and carbon atoms are represented as black spheres. The diagram is divided into upper and lower halves by a horizontal dashed line. At the top left, a CO molecule is shown striking an O subscript 2 molecule, such that the O atom from the CO molecule is at the point of collision. Surrounding this collision are a mix of molecules of CO and O subscript 2 of varying sizes. At the top middle region of the figure, two separated O atoms are shown as red spheres with the label oxygen to oxygen beneath them. To the upper right, no reaction is written. Similarly, in the lower left of the diagram, a CO molecule is shown striking an O subscript 2 molecule, such that the C atom from the CO molecule is at the point of collision. Surrounding this collision are a mix of molecules of CO and O subscript 2 of varying sizes. At the lower middle region of the figure, a black sphere and a red spheres are shown with the label carbon to oxygen beneath them. To the lower right, more CO subscript 2 formation is written, and three models of CO subscript 2 composed each of a single central black sphere, and two red spheres in a linear arrangement are shown. Figure 12.13 illustrated are two collisions that might take place between carbon monoxide and oxygen molecules. The orientation of the colliding molecules partially determines whether a reaction between the two molecules will occur. If the collision does take place with the correct orientation, there is still no guarantee that the reaction will proceed to form carbon dioxide. In addition to a proper orientation, the collision must also occur with sufficient energy to result in product formation. When reactant species collide with both proper orientation and adequate energy, they combine to form an unstable species called an activated complex or a transition state. These species are very short-lived and usually undetectable by most analytical instruments. In some cases, sophisticated spectral measurements have been used to observe transition states. Collision theory explains why most reaction rates increase as concentrations increase. With an increase in the concentration of any reacting substance, the chances for collisions between molecules are increased because there are more molecules per unit of volume. More collisions mean a faster reaction rate, assuming the energy of the collisions is adequate. Activation energy and the Arrhenius equation, the minimum energy necessary to form a product during a collision between reactants, is called the activation energy, E. How this energy compares to the kinetic energy provided by colliding reactant molecules is a primary factor affecting the rate of a chemical reaction. If the activation energy is much larger than the average kinetic energy of the molecules, the reaction will occur slowly since only a few fast-moving molecules will have enough energy to react. If the activation energy is much smaller than the average kinetic energy of the molecules, a large fraction of molecules will be adequately energetic and the reaction will proceed rapidly. Figure 12.14 shows how the energy of a chemical system changes as it undergoes a reaction, converting reactants to products according to the equation letter 1d434 plus letter 1d435 letter 1d436 plus letter 1d437. These reaction diagrams are widely used in chemical kinetics to illustrate various properties of the reaction of interest. Viewing the diagram from left to right, the system initially comprises reactants only. A plus B reactant molecules with sufficient energy can collide to form a high-energy activated complex or transition state. The unstable transition state can then subsequently decay to yield stable products. C plus D, the diagram depicts the reaction's activation energy. E as the energy difference between the reactants and the transition state. Using a specific energy, the enthalpy, see chapter on thermochemistry. The enthalpy change of the reaction, delta, is estimated as the energy difference between the reactants and products. In this case, the reaction is exothermic delta 0 since it yields a decrease in system enthalpy. A graph is shown with the label extent of reaction on the x-axis and the label energy on the y-axis. Above the x-axis, a portion of a curve is labeled A plus B. From the right end of this region, the concave down curve continues upward to reach a maximum near the height of the y-axis. The peak of this curve is labeled transition state. A double-sided arrow extends from a dashed red horizontal line that originates at the y-axis at a common endpoint with the curve to the peak of the curve. This arrow is labeled E subscript A. A second horizontal red dashed line segment is drawn from the right end of the black curve, left to the vertical axis at a level significantly lower than the initial, a plus B, labeled end of the curve. The end of the curve that is shared with this segment is labeled C plus D. The curve, which was initially dashed, continues as a solid curve from the maximum to its endpoint at the right side of the diagram. A second double-sided arrow is shown. This arrow extends between the two dashed horizontal lines and is labeled capital delta H, figure 12. 14 reaction diagram for the exothermic reaction letter 1D434 plus letter 1D435 letter 1D436 plus letter 1D437. The Arrhenius equation relates the activation energy and the rate constant, K, for many chemical reactions. Letter 1D458 equals letter 1D434 letter 1D452 minus letter 1D438 a slash letter 1D445 letter 1D447 in this equation. R is the ideal gas constant, which has a value 8. 314 J/mol/K. T is temperature on the Kelvin scale. E is the activation energy in joules per mole. E is the constant too. 7183, and is a constant called the frequency factor, which is related to the frequency of collisions and the orientation of the reacting molecules. Postulates of collision theory are nicely accommodated by the Arrhenius equation. The frequency factor, A, reflects how well the reaction conditions favor properly oriented collisions between reactant molecules. An increased probability of effectively oriented collisions results in larger values for and faster reaction rates. The exponential term, E minus E/RT, describes the effect of activation energy on reaction rate. According to kinetic molecular theory, see chapter on gases, the temperature of matter is a measure of the average kinetic energy of its constituent atoms or molecules. The distribution of energies among the molecules composing a sample of matter at any given temperature is described by the plot shown in figure 12. 15. A. Two shaded areas under the curve represent the numbers of molecules possessing adequate energy, RT, to overcome the activation barriers, E. A lower activation energy results in a greater fraction of adequately energized molecules and a faster reaction. The exponential term also describes the effect of temperature on reaction rate. A higher temperature represents a correspondingly greater fraction of molecules possessing sufficient energy, RT, to overcome the activation barrier, E, as shown in figure 12. 15b. This yields a greater value for the rate constant and a correspondingly faster reaction rate. Two graphs are shown each with an x-axis label of kinetic energy and a y-axis label of fraction of molecules. Each contains a positively skewed curve indicated in red that begins at the origin and approaches the x-axis at the right side of the graph. In a small area under the far right end of the curve is shaded orange. An arrow points down from above the curve to the left end of this region where the shading begins. This arrow is labeled higher activation energy, E subscript A in B. The same red curve appears, and a second curve is drawn in black. It is also positively skewed, but reaches a lower maximum value and takes on a broadened appearance as compared to the curve in red. In this graph, the red curve is labeled T subscript 1 and the black curve is labeled T subscript 2. In the open space at the upper right on the graph is the label T subscript 1 less than T subscript 2. As with the first graph, the region under the curves at the far right is shaded orange, and a downward arrow labeled E subscript points to the left end of this shaded region. Figure 12. 15 molecular energy distributions showing numbers of molecules with energies exceeding A. Two different activation energies at a given temperature, and B. A given activation energy at two different temperatures. A convenient approach for determining E for a reaction involves the measurement of K at two or more different temperatures, and using an alternate version of the Arrhenius equation that takes the form of a linear equation ln letter 1d458 letter 1d466 equals minus letter 1d438 a letter 1d445 1 letter 1d447 plus ln letter 1d434 letter 1d45 letter 1d465 plus letter 1d44f. Plot of ln k versus 1t is linear with a slope equal to minus letter 1d438 a letter 1d445 and a y-intercept equal to ln a. Example 12. 13 determination of E, the variation of the rate constant with temperature for the decomposition of high G to H2, G and I2, G is given here. What is the activation energy for the reaction? 2 high letter 1d454, H2 letter 1d454, plus 2 letter 1d454 T, K, K, L slash mol slash S, 555 3. 52 times 10 minus 7 575 1. 22 times 10 minus 6 645 8. 59 times 10 minus 5 701. 16 times 10 minus 3 780. 1 395 times 10 minus 2. Solution. Use the provided data to derive values of 1t and ln k. 1t k minus 1, ln k 180 times 10 minus 3 minus 14. 861. 74 times 10 minus 3 minus 13. 617 1. 55 times 10 minus 3 minus 9. 362 1. 43 times 10 minus 3 minus 6. 759 1. 28 times 10 minus 3 minus 3. 231 Figure 12. 16 is a graph of ln k versus 1t in practice, the equation of the line, slope, and y-intercept that best fits these plotted data points would be derived using a statistical process called regression. This is helpful for most experimental data because a perfect fit of each data point with the line is rarely encountered. For the data here, the fit is nearly perfect, and the slope may be estimated using any two of the provided data pairs. Using the first and last data points permits estimation of the slope. A graph is shown with the label 1 divided by t, k superscript -1, on the x-axis, and ln k on the y-axis. The horizontal axis has markings at 1 4 times 10 superscript -3, 1 6 times 10 superscript -3, and 1 8 times 10 superscript -3. The y-axis shows markings at intervals of 2 from -14 through -2. A decreasing linear trend line is drawn through 5 points at the coordinates. 1. 28 times 10 superscript -3, -3 231, 143 times 10 superscript -3, -6. 759, 1. 55 times 10 superscript -3, -9 362, 174 times 10 superscript -3, -13. 617, and 1. 80 times 10 superscript -3, -14. 860. A vertical dashed line is drawn from a point just left of the data point nearest the y-axis. Similarly, a horizontal dashed line is drawn from a point just above the data point closest to the x-axis. These dashed lines intersect to form a right triangle with a vertical leg label of capital delta ln k and a horizontal leg label of capital delta 1 divided by t. Figure 12. 16. This graph shows the linear relationship between ln k and 1t for the reaction 2 high H2 plus 2 according to the Arrhenius equation. Slope letter 1d438 equals delta, ln letter 1d458 delta, 1 letter 1d447, minus 14. 860 minus 3, 231, 1. 80 times 10 minus 3 k minus 1 minus 1. 28 times 10 minus 3 k minus 1 minus 11. 6290. 52 times 10 minus 3 k minus 1 equals 2. 2 times 104 k minus letter 1d438, a letter 1d445 minus slope times letter 1d445 equals minus 2. 2 times 104 k times 8. 314 j mol minus 1 k minus 1. 1. 8 times 105 j mol minus 1 or 180 k j mol minus 1 alternative approach. A more expedient approach involves deriving activation energy from measurements of the rate constant at just 2 temperatures. In this approach, the Arrhenius equation is rearranged to a convenient two-point form. ln letter 1d458, 1 letter 1d458, 2 equals letter 1d438, a letter 1d445. 1 letter 1d447, 2 minus 1 letter 1d4471. 1. Rearranging this equation to isolate activation energy yields. Letter 1d438 equals minus letter 1d445. ln letter 1d458 2 minus ln letter 1d458 1, 1 letter 1d447 2 minus 1 letter 1d4471. Any two data pairs may be substituted into this equation. For example, the first and last entries from the above data table. Letter 1D438 A equals minus 8. 314J mol minus 1 K minus 1 minus 3. 231 minus 14. 860, 1. 28 times 10 minus 3 K minus 1 minus 1. 80 times 10 minus 3 K minus 1. And the result is E equals 18 times 105 J mol minus 1 or 180 kJ mol minus 1. This approach yields the same result as the more rigorous graphical approach used above, as expected. In practice, the graphical approach typically provides more reliable results when working with actual experimental data. Check you're learning the rate constant for the rate of decomposition of N2O 5 to no, and O2 in the gas phase is 1. 66 L/mol/s at 650 K and 739 L/mol/s at 700 K. 2 N2O 5, letter 1D454, 4 no, letter 1D454, plus 3 O2, letter 1D454. Assuming the kinetics of this reaction are consistent with the Arrhenius equation, calculate the activation energy for this decomposition. Answer: 1 times 105 J mol minus 1 or 110 kJ mol minus 1. Learning objectives. By the end of this section, you will be able to distinguish net reactions from elementary reactions. Steps: identify the molecularity of elementary reactions. Write a balanced chemical equation for a process given its reaction mechanism. Derive the rate law consistent with a given reaction mechanism. Chemical reactions very often occur in a stepwise fashion, involving two or more distinct reactions taking place in sequence. A balanced equation indicates what is reacting and what is produced, but it reveals no details about how the reaction actually takes place. The reaction mechanism, or reaction path, provides details regarding the precise, step-by-step process by which a reaction occurs. The decomposition of ozone, for example, appears to follow a mechanism with two steps. O3 letter 1D454, O2 letter 1D454, plus U plus O3 letter 1D4542, O2 letter 1D454. Each of the steps in a reaction mechanism is an elementary reaction. These elementary reactions occur precisely as represented in the step equations, and they must sum to yield the balanced chemical equation representing the overall reaction. 2O3, letter 1D454, 3O2, letter 1D454. Notice that the oxygen atom produced in the first step of this mechanism is consumed in the second step, and therefore does not appear as a product in the overall reaction. Species that are produced in one step and consumed in a subsequent step are called intermediates. While the overall reaction equation for the decomposition of ozone indicates that 2 molecules of ozone react to give 3 molecules of oxygen, the mechanism of the reaction does not involve the direct collision and reaction of 2 ozone molecules. Instead, 1O3 decomposes to yield O2 and an oxygen atom, and a second O3 molecule subsequently reacts with the oxygen atom to yield 2 additional O2 molecules. Unlike balanced equations representing an overall reaction, the equations for elementary reactions are explicit representations of the chemical change taking place. The reactant, S, in an elementary reactions equation undergo only the bond breaking and/or making events depicted to yield the product, S. For this reason, the rate law for an elementary reaction may be derived directly from the balanced chemical equation describing the reaction. This is not the case for typical chemical reactions, for which rate laws may be reliably determined only via experimentation. Unimolecular elementary reactions. The molecularity of an elementary reaction is the number of reactant entities, atoms, molecules, or ions. For example, a unimolecular reaction involves the reaction of a single reactant entities to produce one or more molecules of product. Letter 1D434 products. The rate law for a unimolecular reaction is first order. Rate equals letter 1D458, letter 1D434. A unimolecular reaction may be one of several elementary reactions in a complex mechanism. For example, the reaction O3O2 plus O illustrates a unimolecular elementary reaction that occurs as one part of a two-step reaction mechanism as described above. However, some unimolecular reactions may be the only step of a single-step reaction mechanism. In other words, an overall reaction may also be an elementary reaction in some cases. For example, the gas phase decomposition of cyclobutane, C4H8, to ethylene, C2H4, is represented by the following chemical equation. In this figure, structural formulas are used to illustrate a chemical reaction. On the left, a structural formula for cyclobutane is shown. This structure is composed of 4 C atoms connected with single bonds in a square shape. Each C atom is bonded to 2 other C atoms in the structure, leaving 2 bonds for H atoms pointing outward above, below, left, and right. An arrow points right to 2 identical ethane molecules with a plus symbol between them. Each of these molecules contains 2 C atoms connected with a double bond oriented vertically between them. The C atom at the top of these molecules has H atoms bonded above to the right and left. Similarly, the lower C atom has 2 H atoms bonded below to the right and left. This equation represents the overall reaction observed, and it might also represent a legitimate unimolecular elementary reaction. The rate law predicted from this equation, assuming it is an elementary reaction, turns out to be the same as the rate law derived experimentally for the overall reaction, namely, one showing first-order behavior. Rate equals minus delta C, 4H8 delta letter 1D461 equals letter 1D458C, 4H8. This agreement between observed and predicted rate laws is interpreted to mean that the proposed unimolecular, single-step process is a reasonable mechanism for the butadiene reaction. Bimolecular elementary reactions. A bimolecular reaction involves 2 reactant entities, for example, letter 1D434 plus letter 1D435 products and letter 1D434 products. For the first type, in which the 2 reactant molecules are different, the rate law is first order in A and first order in B, second order overall. Rate equals letter 1D458 letter 1D434 letter 1D435. For the second type, in which 2 identical molecules collide and react, the rate law is second order in A. Rate equals letter 1D458 letter 1D434 letter 1D434 equals letter 1D458 letter 1D434 Some chemical reactions occur by mechanisms that consist of a single bimolecular elementary reaction. One example is the reaction of nitrogen dioxide with carbon monoxide. No2, letter 1D454, plus Co, letter 1D454 No, letter 1D454, plus Co2, letter 1D454. See Figure 12. 17. This figure provides an illustration of a reaction between 2 HI molecules using space-filling models. H atoms are shown as white spheres, and I atoms are shown as purple spheres. On the left, 2 HI molecules are shown with a small white sphere bonded to a much larger purple sphere. The label, 2 HI molecules, appears below. An arrow points right to a similar structure in which the 2 molecules appear pushed together so that the purple spheres of the 2 molecules are touching. Below appears the label, transition state. Following another arrow, 2 white spheres are shown vertically oriented and bonded together with the label, H subscript 2 above. The H subscript 2 molecule is followed by a plus sign and 2 purple spheres bonded together with the label, I subscript 2 above. Below these structures is the label, hydrogen iodide molecules decompose to produce hydrogen H subscript 2 and iodine I subscript 2. Figure 12. 17. The probable mechanism for the reaction between No2 and Co to yield No and Co2. Bimolecular elementary reactions may also be involved as steps in a multi-step reaction mechanism. The reaction of atomic oxygen with ozone is the second step of the 2-step ozone decomposition mechanism discussed earlier in this section. O letter 1D454 plus O3, letter 1D4542, O2, letter 1D454. Termolecular elementary reactions. An elementary termolecular reaction involves the simultaneous collision of 3 atoms, molecules, or ions. Termolecular elementary reactions are uncommon because the probability of 3 particles colliding simultaneously is less than 1/1000th of the probability of 2 particles colliding. There are, however, a few established termolecular elementary reactions. The reaction of nitric oxide with oxygen appears to involve termolecular steps. 2 No plus O2 2 No to rate equals letter 1D458 No 2O2. Likewise, the reaction of nitric oxide with chlorine appears to involve termolecular steps. 2 No plus Cl2 2 No Cl rate equals letter 1D458 No 2Cl2. Relating reaction mechanisms to rate laws. It's often the case that one step in a multi-step reaction mechanism is significantly slower than the others. Because a reaction cannot proceed faster than its slowest step, this step will limit the rate at which the overall reaction occurs. The slowest step is therefore called the rate-limiting step, or rate-determining step, of the reaction figure 12. 18. A photo is shown of cattle passing through a narrow chute into a holding pen. A person directs them through the gate with a long white and red pole. Figure 12. 18. A cattle chute is a non-chemical example of a rate-determining step. Cattle can only be moved from one holding pen to another as quickly as one animal can make its way through the chute. Credit, Lure and Kearns. As described earlier, rate laws may be derived directly from the chemical equations for elementary reactions. This is not the case, however, for ordinary chemical reactions. The balanced equations most often encountered represent the overall change for some chemical system, and very often this is the result of some multi-step reaction mechanisms. In every case, the rate law must be determined from experimental data, and the reaction mechanism subsequently deduced from the rate law, and sometimes from other data. The reaction of NO2 and CO provides an illustrative example. NO2, letter 1D454 plus CO, letter 1D454, CO2, letter 1D454, plus NO, letter 1D454. For temperatures above 225 degrees C, the rate law has been found to be rate equals letter 1D458 NO2 CO. The reaction is first order with respect to NO2 and first order with respect to CO. This is consistent with a single-step bimolecular mechanism, and it is possible that this is the mechanism for this reaction at high temperatures. At temperatures below 225 degrees C, the reaction is described by a rate law that is second order with respect to NO2. Rate equals letter 1D458 No 22. This rate law is not consistent with the single-step mechanism, but is consistent with the following two-step mechanism. NO2, letter 1D454 plus NO2, letter 1D454 No 3, letter 1D454, plus No, letter 1D454. Slow No 3, letter 1D454 plus CO, letter 1D454 No 2, letter 1D454, plus CO 2, letter 1D454. Fast. The rate determining, slower step gives a rate law showing second-order dependence on the NO2 concentration, and the sum of the two equations gives the net overall reaction. In general, when the rate-determining, slower step is the first step in a mechanism, the rate law for the overall reaction is the same as the rate law for this step. However, when the rate-determining step is preceded by a step involving a rapidly reversible reaction, the rate law for the overall reaction may be more difficult to derive. As discussed in several chapters of this text, a reversible reaction is at equilibrium when the rates of the forward and reverse processes are equal. Consider the reversible elementary reaction in which NO dimerizes to yield an intermediate species N2O2. When this reaction is at equilibrium, NO plus NO N2O2 rate forward equals R a T, ER, EV, ER, S, E letter 1D458, 1 NO2 equals letter 1D458 minus 1 N2O2. This expression may be rearranged to express the concentration of the intermediate in terms of the reactant NO. K1 NO2, K minus 1 equals N2O2. Since intermediate species concentrations are not used in formulating rate laws for overall reactions, this approach is sometimes necessary, as illustrated in the following example exercise. Example 12.14. Deriving a rate law from a reaction mechanism. The two-step mechanism below has been proposed for a reaction between nitrogen monoxide and molecular chlorine. Step 1. NO letter 1D454 plus Cl2 letter 1D454 NaCl 2 letter 1D454 step 2. NaCl 2 letter 1D454 plus NO letter 1D454 2 NaCl letter 1D454 fasts. Use this mechanism to derive the equation and predicted rate law for the overall reaction. Solution. The equation for the overall reaction is obtained by adding the two elementary reactions. 2 no, letter 1d454, plus Cl2, letter 1d454, 2 knuckle, letter 1d454. To derive a rate law from this mechanism, first write rates laws for each of the two steps. Rate 1 rate minus 1 rate 2 equals letter 1d458, 1 no Cl24, the forward reaction of step 1 letter 1d458, minus 1 knuckle 24, the reverse reaction of step 1 letter 1d458 2 knuckle 2 no 4, step 2. Step 2 is the rate determining step, and so the rate law for the overall reaction should be the same as for this step. However, the step 2 rate law, as written, contains an intermediate species concentration, knuckle 2. To remedy this, use the first step's rate laws to derive an expression for the intermediate concentration in terms of the reactant concentrations, assuming step 1 is at equilibrium. Rate 1 letter 1d458 1 no Cl 2 knuckle 2 equals rate minus 1 letter 1d458 minus 1 knuckle 2 no Cl2. Substituting this expression into the rate law for step 2 yields rate 2 equals rate overall equals letter 1d458 to letter 1d458 1 letter 1d458 minus 1 no 2 Cl2. Check your learning. The first step of a proposed multi-step mechanism is F2 letter 1d4542, F letter 1d454 fast. Derive the equation relating atomic fluorine concentration to molecular fluorine concentration. Answer: F equals letter 1d458 1 F2 letter 1d458 minus 1, 1/2. Learning objectives. By the end of this section, you will be able to explain the function of a catalyst in terms of reaction mechanisms and potential energy diagrams, list examples of catalysis in natural and industrial processes. Among the factors affecting chemical reaction rates discussed earlier in this chapter was the presence of a catalyst, a substance that can increase the reaction rate without being consumed in the reaction. The concepts introduced in the previous section on reaction mechanisms provide the basis for understanding how catalysts are able to accomplish this very important function. Figure 12:19 shows reaction diagrams for a chemical process in the absence and presence of a catalyst. Inspection of the diagrams reveals several traits of these reactions. Consistent with the fact that the two diagrams represent the same overall reaction, both curves begin and end at the same energies. In this case, because products are more energetic than reactants, the reaction is endothermic. The reaction mechanisms, however, are clearly different. The uncatalyzed reaction proceeds via a one-step mechanism, one transition state observed, whereas the catalyzed reaction follows a two-step mechanism, two transition states observed, with a notably lesser activation energy. This difference illustrates the means by which a catalyst functions to accelerate reactions, namely, by providing an alternative reaction mechanism with a lower activation energy. Although the catalyzed reaction mechanism for a reaction needn't necessarily involve a different number of steps than the uncatalyzed mechanism, it must provide a reaction path whose rate determining step is faster, lower e's. A graph is shown with the label extent of reaction, appearing in a right-pointing arrow below the x-axis and the label energy in an upward-pointing arrow just left of the y-axis. Approximately 1/5 of the way up the y-axis, a very short, somewhat flattened portion of both a red and a blue curve are shown. This region is labeled reactants. A red concave down curve extends upward to reach a maximum near the height of the y-axis. From the peak, the curve continues downward to a second horizontally flattened region at a height of about 1/3 the height of the y-axis. This flattened region is labeled products. A second curve is drawn in blue with the same flattened regions at the start and end of the curve. The height of this curve is about 2/3 the height of the first curve and just right of its maximum. The curve dips low, then rises back and continues a downward trend at a lower height, but similar to that of the red curve. A horizontal dashed straight line extends from the point where both curves start in the reactants region. A double-sided arrow extends from the products region at the end of both curves to this horizontal dashed line. This is labeled capital delta H. A double-sided arrow extends from the dashed horizontal line to the peak of the red concave down curve. This arrow is labeled E subscript A. Another double-sided arrow extends from the dashed horizontal line to the peak of the blue curve. This arrow is labeled E subscript A, figure 12. 19 reaction diagrams for an endothermic process in the absence, red curve, and presence, blue curve, of a catalyst. The catalyzed pathway involves a two-step mechanism. Note the presence of two transition states and an intermediate species represented by the valley between the two transition states. Example 12. 15 reaction diagrams for catalyzed reactions. The two reaction diagrams here represent the same reaction, one without a catalyst and one with a catalyst. Estimate the activation energy for each process and identify which one involves a catalyst. In this figure, two graphs are shown. The x-axes are labeled extent of reaction, and the y-axes are labeled energy, kJ. The y-axes are marked off from 0 to 50 in intervals of 5. In A blue curve is shown. It begins with a horizontal segment at about 6. The curve then rises sharply near the middle to reach a maximum of about 32 and similarly falls to another horizontal segment at about 10. In B, the curve begins and ends similarly, but the maximum reached near the center of the graph is only 20. Solution activation energies are calculated by subtracting the reactant energy from the transition state energy. Diagram A. Letter 1 D438 A equals 32 kJ minus 6 kJ equals 26 kJ. Diagram B. Letter 1 D438 A equals 20 kJ minus 6 kJ equals 14 kJ. The catalyzed reaction is the one with lesser activation energy, in this case represented by diagram B. Check your learning reaction diagrams for a chemical process with and without a catalyst are shown below. Both reactions involve a two-step mechanism with a rate-determining first step. Compute activation energies for the first step of each mechanism and identify which corresponds to the catalyzed reaction. How do the second steps of these two mechanisms compare? In this figure, two graphs are shown. The x-axes are labeled extent of reaction, and the y-axes are labeled energy, kJ. The y-axes are marked off from 0 to 100 at intervals of 10. In a blue curve is shown. It begins with a horizontal segment at about 10. The curve then rises sharply near the middle to reach a maximum of about 91, then sharply falls to about 52, again rises sharply to about 73 and falls to another horizontal segment at about 5. In B, the curve begins and ends similarly, but the first peak reaches about 81, drops to about 55, then rises to about 77 before falling to the horizontal region at about 5. Answer. For the first step, E equals 80 kJ for A and 70 kJ for B, so diagram B depicts the catalyzed reaction. Activation energies for the second steps of both mechanisms are the same, 20 kJ. Homogeneous catalysts. A homogeneous catalyst is present in the same phase as the reactants. It interacts with a reactant to form an intermediate substance, which then decomposes or reacts with another reactant in one or more steps to regenerate the original catalyst and form product. As an important illustration of homogeneous catalysis, consider the Earth's ozone layer. Ozone in the upper atmosphere, which protects the Earth from ultraviolet radiation, is formed when oxygen molecules absorb ultraviolet light and undergo the reaction. 3O2, letter 1D454, minus right minus minus, letter 210, letter 1D4630, letter 1D454. Ozone is a relatively unstable molecule that decomposes to yield diatomic oxygen by the reverse of this equation. This decomposition reaction is consistent with the following two-step mechanism. O, a number of substances can catalyze the decomposition of ozone. For example, the nitric oxide. Catalyzed decomposition of ozone is believed to occur via the following three-step mechanism. No, letter 1D454 plus O3, letter 1D454 no. 2, letter 1D454 plus O2, letter 1D454 O3. Letter 1D4540, 2 letter 1D454 plus. O letter 1D454 no, 2 letter 1D454 plus. O letter 1D454 no. Letter 1D454 plus. O2 letter 1D454 as required. The overall reaction is the same for both the two-step uncatalyzed mechanism and the three-step no-catalyzed mechanism. 2O3, letter 1D454, 3O2, letter 1D454, Notice that No is a reactant in the first step of the mechanism and a product in the last step. This is another characteristic trait of a catalyst. Though it participates in the chemical reaction, it is not consumed by the reaction. Portrait of a Chemist Mario J. Molina, the 1995 Nobel Prize in Chemistry, was shared by Paul J. Crutzen, Mario J. Molina, Figure 12. 20, and F. Sherwood Rowland for their work in atmospheric chemistry, particularly concerning the formation and decomposition of ozone. Juan Molina, a Mexican citizen, carried out the majority of his work at the Massachusetts Institute of Technology, MIT. A photograph is shown of Mario Molina. To the right of the photo, an image of Earth's southern hemisphere is shown with a central circular region in purple with a radius of about half that of the entire hemisphere. Just outside this region is a narrow royal blue band, followed by an outer thin turquoise blue band. The majority of the outermost region is green. Two small bands of yellow are present in the lower regions of the image. Figure 12. 20a Mexican chemist Mario Molina, 1943, 2020, shared the Nobel Prize in Chemistry in 1995 for his research on B, the Antarctic ozone hole. Credit A. Courtesy of Mario Molina. Credit B. Modification of work by NASA. In 1974, Molina and Rowland published a paper in the journal Nature detailing the threat of chlorofluorocarbon gases to the stability of the ozone layer in Earth's upper atmosphere. The ozone layer protects Earth from solar radiation by absorbing ultraviolet light. As chemical reactions deplete the amount of ozone in the upper atmosphere, a measurable hole forms above Antarctica and an increase in the amount of solar ultraviolet radiation